Coming up next, an Astronomy.fm original program. It's time for York Universe, a co-production of the Observatory of York University, Toronto, and the Voice of
Hello,
Astronomy.
and welcome to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'm Julie Tomei. I will be one of your hosts this evening, and I will be joined by Kshitij Govil and Connor Hayes. Good evening, both.
Hello.
Good evening.
Broadcasting. Hey, we are broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. This is Astronomy Night in Canada, where the lineup is all Canadian, starting with ourselves, York Universe, then on to Western Worlds, Quirks and Quarks, and Science for the People. York Universe broadcasts every Monday night at 9 p.m. local Toronto time or Tuesday morning at 2 a.m. UT. The York Universe production works in concert with our online public viewing program run by the Observatory team, which runs between the hours of 9 and 10 p.m. local Toronto time. If you want to join that, you can head over to our website, observatory.info.yorku.ca, and follow the links to online public viewing. And join in the chat. Our broadcast is powered by and in partnership with Astronomy.fm, the voice of astronomy. For any questions or comments you have about our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on the socials. We are at York Observatory on Twitter and Instagram, and you can also find us on Facebook at Alan I. Carswell Observatory. All of our programs are free, but if you would like to make a donation, we won't turn you down. Please visit our website. Again, that is observatory.info.yorku.ca. We'll be monitoring the chat room for questions, post any content. The current weather, and I have here in my notes, it says blah, and that is accurate. We have been receiving quite a load of snow in the GTA this evening. So, Connor, Kshitij, how are you doing?
I'm pretty good. I've definitely been enjoying, the ample amount of snow that we've had.
It's quite something, and I'm a little further north, so I don't think I've gotten as much as the city of Toronto. It's like Toronto proper has gotten. There's been lots of fun photos for me to look at.
Yeah, I took a short bit of a hike through it earlier today, and some of the larger snowdrifts were coming up above my knees. If that gives you any sense of how much snow there is.
That does give me a sense. I hope you either have snow pants or like gaiters or.
Oh yeah, I'm all good.
No, just snow in the boots, huh?
That's a good title for a movie. Snow in the Boots.
All right. Well, it's not a Canadian winter without a good dumping of snow, I guess.
It's true, absolutely true.
Yeah. But without further ado, we have quite a lot in our program today, so let's jump in. We will start, as always, with this week and in space and astronomy history. Go ahead, Connor.
All right, thank you. So on January, we will begin with January 19th, 2006. This marked the launch of the New Horizons spacecraft. So following the Voyager 2 flyby of Neptune in August of 1989, Pluto became the only planet in our solar system that had not yet been studied at close range. Consequently, during the 90s, NASA proposed a number of missions to Pluto, which culminated in the formation of the New Horizons team in December of 2000. Less than a year later, in November 2001, New Horizons was selected as the first mission in what would become the New Frontiers program. However, the mission found itself fighting for its life almost immediately because the newly named NASA administrator, Sean O'Keefe, was not a fan of the mission, going so far as to zero out its budget in the Bush administration's 2003 federal budget request. Needless to say, the planetary science community was not exactly pleased with this, and subsequently named a Pluto mission as the top priority among medium-sized missions in the 2003 to 2013 Planetary Science Decadal Survey. Shortly thereafter, the mission's budget was restored. So after the launch, given how far it had to travel, it wasted no time hanging around Earth, launching directly into a solar escape trajectory at 16.26 kilometers per second, which was a higher initial velocity than any other man-made object. Also, New Horizons' only close encounter with a large solar system body occurred over the course of about 6 months in early 2007, as the spacecraft used Jupiter to perform a gravity-assisted course correction. As it flew by, it gathered data on Jupiter's atmosphere, and it took photos of the 4 Galilean moons. In 2011, the discovery of 2 new moons, Kerberos and Styx, raised some concerns that the near Pluto environment might be too dangerous for New Horizons. Fortunately, after 18 months of computer simulations and many, many hours of ground-based observations, it was concluded that the chance of a catastrophic collision occurring between the spacecraft and orbital debris was minimal, so the mission continued as planned. New Horizons finally flew through the Pluto system 9.5 years after launch on July 14th, 2015. Just a week and a half before closest approach, the success of the mission was imperiled by a software glitch that shut down all of the spacecraft's scientific instrument. Given that the result of a decade and a half of work was riding on their shoulders, NASA's software engineers successfully fixed the problem with just a week to spare. The mission returned beautiful photos of Pluto and its 5 moons, successfully completing its primary mission, even though Pluto was no longer the final unexplored planet, as it had been reclassified as a dwarf planet only 7 months after New Horizons was launched. In its extended mission, New Horizons became the first spacecraft to explore an object that had not yet been discovered before launch, when it flew by the Kuiper Belt object 486958 Arrokoth on January 1st, 2019. With enough power to continue operating until some point in the 2030s, New Horizons has sufficient time left in its life to perform one final flyby of another Kuiper Belt object. However, at this moment, no ideal targets have been identified.
Oh, New Horizons. I love that mission.
It's definitely one of those things that it just went on for so long that it sort of, took up a lot of my, consciousness in my early life.
Yeah. I was at York.
Oh yeah.
Go ahead, Satish.
Now I was just saying, are you like a fan of the mission, or a fan of the fact that they reached where they reached? Interviewing you, like adding to the mix.
I just think, it's always, it was just nice, actually to finally have photos of Pluto, because it's sort of incredible that we had this, what at the time was a planet, and we just had no idea what it looked like.
Yeah. I mean, it did involve Pluto. That's the reason, my ears go up, like trying to listen to everything related to Pluto. And that's all the recollection that I have related to New Horizons, which is why I keep asking people, what else? That's it.
Pluto was always so mysterious, right? This tiny, when I was growing up, 9th planet. And actually, when I started learning about astronomy, it wasn't the 9th planet, it was actually the 8th, because of its weird orbit that actually takes it closer to the sun than Neptune for a little part of its trip around the sun. The flyby was an opportunity for me to bring my daughter to one of these events. Like, they were having an event at York, and so And she was 6 at the time. And so I just remember sitting in there in the room with everyone, everyone kind of with bated breath, like, and it's not like images came back, right? It was just like a signal that was like, yep, I'm here. But it was still so exciting. Like it was like electric in the room. And she was at an age where, I would spend a lot of time laying next to her while she was falling asleep and like drawing pictures on her back, right? And so once we did get that image of Pluto back, I would always be like drawing a little circle with the heart in it, right? And she'd be like, that's Pluto.
Amazing. So, well, basically then your generation will actually have nice stories to tell, and your daughter's generation also will have nice stories to tell, better than the ones which the people from 20th century could say. I'm just rubbing it in their face. I don't know why, but it's trying to be funny.
You didn't know it was there.
Exactly. I mean, well, let's hear someday. Let's hear what Professor Delaney has to say, of course. I mean, he's got wonderful stories, of course. So I'm just trying to be funny as I can be.
There's just so many like interesting beats to the story of this mission about it almost like not happening, and then the launch happening, and then a few months later the infamous meeting where Pluto was reclassified and people are still up in arms about it, to everything shutting down when they were almost there. Like I can't imagine what it would have been like to be one of those software engineers. Like you got a deadline and it's a drop deadline. Like
well,
all right. So let's move on to our next piece of this week in history. We are going to January 22nd, 1992. So this is a 30-year anniversary of Roberta Bonder becoming the first female Canadian astronaut. You may have noticed my pronunciation of her name. It is indeed Bonder, not Bondar. Something that was one of the first things she pointed out when I had the opportunity to meet her about 10 years ago. So Saturday. Oh. Yeah, I have. She's so cool.
Okay.
Yeah, I'll tell you about it after I go through this. And so Saturday marks the 30th anniversary of the launch of STS-42, which was a mission of the Space Shuttle Discovery, which carried Roberta Bonder and 6 other crew members to space. Bonder knew from a young age that she wanted to go to space, but she really had to fight to get there. In high school, for instance, her guidance counselor tried to convince her that science was a subject best left to men. She, of course, did not listen, thankfully. Instead, she went on to get a Bachelor of Science in Zoology and Agriculture from the University of Guelph, a Master's of Science in Experimental Pathology from the University of Western Ontario, now known as Western University, a PhD in Neuroscience from the University of Toronto, and an MD from McMaster University. In 1983, at the age of 37, she was selected as one of the first 6 members of the Canadian Astronaut Corps. She eventually was assigned to STS-42 and actually nearly lost her spot on the mission after complaining about how NASA was treating her family. While the other crew members' families were allowed to watch the launch from a room in the vehicle assembly building, Bonder's mother and sister had to watch from the public gallery. And furthermore, she didn't have anyone to greet her at Edwards Air Force Base after returning because the rules at the time stated that astronauts could only be greeted by a spouse or a dog. She had neither. But she did fly, and she became the first neuroscientist and the first Canadian woman to space. And she was also the first Canadian to fly on a space shuttle mission after the Challenger disaster of 1986. Following her space flight, she retired from the Canadian Space Agency, and after retiring, she continued her medical research and stuff, and continued on with a passion for photography that she'd had from a young age, took up wildlife photography, and now studies endangered migratory birds. She's established the Roberta Bonder Foundation that's based here in Toronto in 2009, and the goal of that foundation is to bring art and science back together. At some time in the past, the two were just part of human knowledge, and then we decided at some point to put everything in tidy little boxes, and she feels that's a detriment, and I agree. And I feel like we're starting to see some returning to including arts along with science. If you look at the STEAM, science, technology, engineering, and math, a lot of or STEM, a lot of people add the A in there for arts to make STEAM. I just listened to this evening an interview that she did with Pia Chattopadhyay of the CBC's Sunday Magazine, which was really excellent. So I recommend if you have about a half hour of time to go check that out. So yes, Ksitich, I did have the chance to meet Roberta Bonder. As I said, about 10 years ago, I was working at the Ontario Science Centre at the time. And she was she was at the center. I don't remember exactly why. There was probably an event of some sort. But I was working in the camps department, and the groups were all named after scientists, and so we had a group called Bonder, and so I was one of the coordinators. So I got to meet her along with the counselors for that group. So it was a neat experience. She's a tiny woman and feisty.
Okay, that's a very descriptive image. Is that how you say it? But interesting. I was actually surprised. And maybe I shouldn't be, but is this thing about the spouse or the dog actually true? It doesn't make sense, and that's why I'm asking. Yeah. Of course, I mean, it must be. Of course,
you're right.
It didn't make any sense to me when I read it. I was just reading it was a CBC article about this 30th anniversary, and yeah, that's what they said. They said, yeah, if you're an astronaut returning to Earth, you can only be graded by a spouse or a dog.
That's weird. That's maybe they have medical reasons or something. I mean, therapeutic. I feel like, don't get me wrong. Yeah.
I'm thinking it's probably a holdover from, like the early days of the space program where it was all men, and it was the 60s. So what did you do when you got to your 20s? You got married, had children. The dog part just baffles me because it's like her mother and sister were there. Why is a dog more important? I don't know.
Precisely my point. And they didn't even mention a cat. I mean, cat people will be so annoyed when they read this. It will start another war, maybe.
Insert comment about cats not caring here.
Yes.
I imagine there would also be like a great photo op, right? Like, oh, the dog is so happy his master is back. Whereas the cat would be like,
yeah, whatever. Where's my food?
I'd be interested to see what the rules are now. I imagine that those have changed since then, I hope.
I would think.
I'm crossing fingers. Who knows?
See, that's why I always thought the STS missions were mysterious. It's one of the other reasons, probably. Wow.
You find them mysterious?
No, I'm just saying, and you don't hear me laughing, right? I'm just trying to be unnice to the STS mission every time that I hear about it. So that's just me being rude for no reason. That's it.
I mean, there were so many of them.
Exactly. Yeah. We did cover something last week, and Professor Delaney talked about the STS missions, I guess, the beginning and the end. And I was like, that's the reason I never felt like getting into what those are and why there were so many of them. But I've forgotten that by now, which is a good thing. Right.
I have to say that for a while, like, we've been doing this show for a long time now. And I think
Yes.
that I've been a host for coming on 10 years soon. So, you get to the point where it's like, this week in history, what am I going to do now? And recently, regular listeners may have noticed that I have been digging into the STS missions because there always seems to be, for most of them, some little tidbit of like interesting, like, oh, this was the first this, or this was the last that, or,
Yeah.
So I used to ignore them as well, but I don't ignore them as much now.
Well.
All right. So we have just a few minutes before we bring on our very special guest this evening. So, Ksitich, it wouldn't be this week without birthday shout-outs.
Sure. And I'm happy to bring my, magic back with the first birthday shout-out for the year, because we didn't do it last week. And to begin with, January 18, 1971, let's say happy birthday to Amy J. Barger, an American astronomer who is known for her pioneering works in collating data from multiple telescopes and across multiple wavelengths to discover distant galaxies and supermassive black holes, specifically the ones outside the visible spectrum. And this becomes a teaser of sorts when Professor Muzzin will start talking about things. It is also claimed that her research has overturned current and widely accepted models of how galaxies and supermassive black holes evolve. And this is like recent, I think, maybe in the last couple of years or something. So she is a force. She's maybe one of the forces in current astronomy. No, of course she is. I'm just kidding. And then the second birthday shout out is for Buzz Aldrin. And it goes way back to January 20th, 1930 is when he was born. So happy birthday, Buzz. He got grace. He's alive, and probably the only alive member of the Apollo mission, which went to the moon. I'm sorry I don't remember the number. Well, actually, it was 11. So anyways, he is a former astronaut. He was an engineer and also a pilot. He did 3 spacewalks for the Gemini 12 mission. This was in 1966. And he did 1 count of moonwalk. So you have to understand that this is 1 count, which is a very important count, for the 1969 Apollo 11 mission, of which he was also the lunar module pilot. He even took a photo of his own boot print on the lunar soil on July 21, 1969. Happy birthday to both of them, and happy birthday to all the ones coming in the year later on, because you never know. I might miss someone. Okay.
Excellent. Happy birthday to them both.
Thank you.
All right. So, as I mentioned, we have a guest joining us this evening. Dr. Adam Muzzin is an assistant professor at York University, and his research focuses on galaxy formation and evolution, particularly the highest redshift universe. Dr. Muzzin is also one of the guaranteed Canadian observers on the JWST. Adam, are you there?
Hey, yeah, nice to talk to you guys. How are you doing?
Good, thanks. Thank you so much for joining us.
Happy to hear your voice.
All right. So could you please tell us a little bit about your research?
Yeah, sure. I spend a lot of time with galaxies, And, one of the things we've been trying to do for decades, too many decades, is really understand how galaxies form, right? You look around, we live in this beautiful Milky Way. People tell you there's 100 billion stars in it, which is quite a few. It's a big, beautiful spiral galaxy. And you might ask yourself, how does such a thing get here? And, we know when we look back towards the Big Bang, we see, just the seeds of structure forming, but we don't see galaxies. And we've been really trying to unravel that process of, how you go from just the initial seeds of little density perturbations in the early universe to these, grand galaxies filled with hundreds of billions of stars. And so for myself, I like to study really distant ones. The reason being that light, takes time to travel. So as you look at galaxies that are far away, you effectively have a time machine. And so if you really want to understand the early stages, and I think we're, learning that the early stages of galaxy formation, really a lot happens then you really want to look at distant galaxies and see what's going on. So that's what I've been spending way too much time doing.
So,
yeah, go ahead.
no, I was literally about to talk about JWST specifically. What exactly does it bring you for your research, and like for any listener for that matter, one would want to know what is so special about James Webb, which wasn't available earlier. So, yeah.
Yeah, absolutely. Well, I mean, the short one-word answer is everything. But to expand upon that single word, I mean, James Webb is the culmination of decades of work and billions of dollars in funding. It's really hard to put enough superlatives on it. I mean, I will say this is the greatest telescope built by mankind. There is no question. The Hubble Space Telescope has been an absolute gift to astronomy, and I think your listeners who whenever you see beautiful pictures in astronomy, probably 80% of them come from the Hubble Space Telescope. And with James Webb, what we're doing is we're building on that. And so, in terms of my own research, the James Webb does three things differently than Hubble. And those are, number one, it has a bigger primary mirror. So the kind of what we call angular resolution, or the detail you get, is proportional to how big your primary mirror is. So James Webb takes images that are about 2 to 3 times sharper than Hubble. So we get much sharper images. The other thing that probably a lot of your listeners know who are fans of astronomy is the bigger the mirror, the more light you can collect, and so the fainter of object you can see. And so by having such a much bigger mirror, James Webb allows you to see fainter things. And then lastly, and the real key part for my own research, and well, a lot of research with James Webb, is it's optimized to look into the infrared. And Hubble has a little bit of access to the infrared, the very bluest part of the infrared. But James Webb goes much, much further into the infrared. And if you think about looking for distant galaxies, everything is red shifted. So you want to see the most distant ones, you want to look in the infrared. It's also true of studying planets. Planetary atmospheres are much brighter in the infrared. So this combination of better angular resolution, seeing fainter objects, and also being optimized for the infrared gives us just all sorts of capabilities we didn't dream of having with Hubble, but are really optimized for those two main science goals of looking at the first galaxies, but also, looking at the atmospheres of forming planets. And I think those are two of the most exciting topics in astronomy. So James Webb is poised to just, change everything, really.
And definitely sounds exciting. Go ahead.
And well, I'm just picking up from what he said. So the infrared spectrum, is it fair to ask, even if one was a novice or not into astronomy, that does it enable us, as as has been the buzz, does it enable us better than ever as a human race to look farther back in the universe, which basically means farther back in time and all that, and I mean, you did, of course, touch upon that part already, but why the infrared is something that probably is a question that I did come across on the web when I was listening to the launch sequences and everything, like those videos and all. Mm-hmm. And is there anything better that we can talk about within the time frame, or I should just not go there right now?
Well, I mean, especially as you said, for looking back in time, what happens is the kind of galaxies are brightest in the kind of light that you and I see, because that's the kind of light that stars emit. And as objects get further away, they're moving faster. They're moving away from us faster and faster and faster and faster. And so the wavelengths of light that are the brightest, that our eye sees, are shifted way out into the infrared, further into the infrared than Hubble can see. And so these very distant galaxies, some of the first ones to form, you just cannot see them with Hubble at all. Even if you wanted to, you could take a very long exposure, you could integrate forever, and you would see nothing, because you wouldn't be looking at the right part of the spectrum. And so it's absolutely key for this endeavor. Absolutely key.
Thank you, Professor.
So how does one become a guaranteed Canadian observer on the JWST?
Yeah, good question. So I was only added about three years ago. And, this is a project, so, and there's been tons of people working on this for over 20 years. NASA likes to have partnership in these gigantic flagship missions, of which James Webb, as NASA points out, it's on the same order as the International Space Station, the Space Shuttle. It's a really major mission for NASA. This is not just like another satellite, right? And so they like to have international cooperation, and they have that, right? They have Canadian Space Agency and the European Space Agency launched it on the rocket. So what they did is they asked Canada, do people want to contribute? And Canada contributed an instrument. So there's 4 cameras or instruments, whatever you want to call them, on James Webb, and one of them was built by Canada, PI'd by René Doyon in Montreal. And they spent 20 years working on this camera and assembling it, and it's flying on the spacecraft now. I was fortunate enough to, when I came back to Canada for this job, I have a lot of scientific expertise in doing this. And so one of the things that was given to Canadians, to the team that built NEARIS, was guaranteed access to data. And so I was fortunate enough that the team identified me as a person who can really add a lot of expertise and data analysis skills to all the data that's going to come. There's going to be quite a pile of it. And so they called me up on the phone and said, "Hey, would you like to join the team?" And you can imagine what that was like, right? You get a phone call like, "Hey, would you like to join the team to get guaranteed observations on the greatest telescope built by mankind?" And, you fall out of your chair for a second, and you're on the floor holding the phone, and you say, "Let me think about that for a minute." Yes. And, ever since then, I've been working as part of the team, building software and various other things in order to be ready for the data analysis, including students here at graduate students here at York University. So there's a real York contribution to this team, which is exciting.
That's definitely exciting.
From that standpoint, and again, like I said, I've just picked up these points while sort of following the James Webb launch. In terms of the data that one acquires, the telescope has been positioned at a Lagrange point. And is there anything that you would like to tell our listeners about why the Lagrange point? Why are they special at all in the first place? And why specifically L2 that we've chosen to sort of keep it there?
Mm-hmm. Well, so the Lagrange point is this point in space where the gravitational attraction of the Earth and the Moon and the Sun all basically cancel, okay? And so you're in a sort of effective zero gravity, zero gravitational forces are acting on the spacecraft. And that has all sorts of advantages for, moving the spacecraft around, that it's not feeling additional forces. And many observatories are placed there. But particularly for James Webb, the other reason it needs to be in an orbit like that is the Lagrange point 2 is basically out past the orbit. It's further away from the sun than the Earth and the Moon, and it's out past the Moon's orbit. And if you look at the way the Webb telescope orbits, it has its sun shield facing towards the Earth and the sun at all times. Okay, and that's different than the Hubble Space Telescope. The Hubble Space Telescope is in orbit around the Earth. And so if you think about what that orbit looks like, it comes into the sunlight for half of its orbit, and then it's in the dark for the other half as it continues to go, just like the Earth goes around in 24 hours, the Hubble goes around in about 90 minutes, but it's constantly experiencing this being illuminated and going dark again. James Webb has it so that because it's orbiting in this Lagrange point, it's always facing its sun shield right towards the Earth and right towards the sun. And that is absolutely essential for observing at these infrared wavelengths, because matter, when it's warm, glows, right? Just like, you turn on your stove and you see the stove glowing. Stove is quite hot. But when you're trying to look in the infrared, even cool things, even, things that are, freezing cold to our touch, like minus 50 degrees, they're actually emitting still a little bit of radiation, particularly in the infrared. And so your telescope itself actually glows in the infrared, which is really annoying. It makes it hard to see things because you're like dealing with the glow of your own telescope. And so the key is to keep the telescope absolutely as cold as possible, like in a perfect world, as close to absolute, minus 273 degrees Celsius as you can. And so by having it always facing away from the sun with this super large sun shield, you keep the telescope cold, and that allows you to see fainter objects because you're not, dealing with the glow of your own telescope. So that's why it's in the L2 orbit.
So that actually does bring us to another point that I want to talk about. I heard the phrase steady state temperature, which is what is where the James Webb Telescope is right now. And they did talk about how there's gradual cooling between the layers of the mirrors and the shields as well. But what really interested me was how does it make it different for a ground-based telescope in terms of handling that level of engineering, or for that matter, for the James Webb itself. And I also came across the fact that they have not exactly gold as mirrors. They have beryllium mirrors with a gold coating, and they're using arsenic-doped silicon detectors. So that's like too much detail, of course, probably engineering stuff, material science stuff. But how does that fit into this entire scenario of cooling things or keeping them cool? Or for that matter, how does the steady state temperature phenomena fit in here?
Yeah, well, so the sun shield is it is an impressive piece of engineering because, one of the things about space is we've known this for a long time, astronaut spacesuits, when you're in the sun, the temperature is really hot. And then as soon as you're out of the sun, the temperature is really cold. And, the telescope does see the sun, and it has this sort of 5-layer, very, very thin material sun shield. And what's just beyond impressive in the engineering is the bottom layer of the sun shield, which the sun shines on, can be up to a few hundred degrees Fahrenheit, around 100 degrees Celsius. And then across the other 5 layers, you get to a temperature of, minus 200 degrees Celsius. So there's a 350 degree temperature change as you go across the sun shield. And the sun shield, the layers are about 5 or 6 feet thick. So imagine trying to engineer that in your house, that your floor, is 150, 200 degrees like an oven, and your ceiling, is colder than the coldest night in Winnipeg. You know what I mean?
That's a good visual, yeah.
Yeah, it's not even your ceiling, because your ceiling isn't 5-6 feet tall. It's a few feet below the ceiling. That's an incredible temperature gradient, right? To do so in such a short period of time. And that's why the sun shield is so essential for the telescope and was such a major part of the engineering. In terms of the mirrors, you talk about them being made of beryllium, which is a horribly toxic substance. But the reason you do that is obviously they change in temperatures a lot from the temperature they're built at here on Earth versus, the incredibly cold temperature that they function at. And remember that, astronomical mirrors have to be ground to incredible precision. And so if you build it perfectly here on Earth and then you change its temperature by 300 degrees, you don't want it to warp. And so that's the advantage of beryllium, is that it is one of the most structurally stable components out there in terms of temperature changes. It changes in size and shape almost not at all, even as you change it hundreds of degrees in temperature. And so even though it's this horribly toxic substance that, like, if you touch it, you can get cancer, all that kind of stuff. It's the perfect thing. It's the perfect thing to build the mirror of the telescope out of.
Well, thank you so much, Professor. That's exactly the kind of curiosity I had when I was going through these details. Well, thank you so much. I appreciate it.
So talking about warping of the mirrors, we all know that the primary mirror is made up of a number of smaller segments. And they have to be aligned before the telescope can actually take any data. Do you know, once all the segments are aligned, are they good to go forever, or will the alignment sort of have to be an ongoing process over the lifetime of the telescope?
Yeah, that's a good question. I don't actually know the specific answer. I think, because the whole point of the telescope is incredible stability and temperature and all of that, there's probably no reason to think that they will need to be adjusted. We have similar telescopes on Earth, the very famous Keck telescopes, which, they used to be the largest telescope on Earth. They built one in Spain that's like 2 centimeters bigger, but very similar. But anyway, they are, they are amongst the largest telescopes on Earth, and they're of the same construction. They're a segmented mirror. And, we realign those all the time because the temperature is constantly changing, right? The Keck telescopes are on Mauna Kea in Hawaii, and, sometimes it's really cold there, sometimes it's really warm. But, James Webb is going to stay stable. So I think in a perfect world, the hope would be that the number of adjustments that they have to make over the lifetime is, minor to perhaps not at all. But we'll have to see.
Thank you. As we know, the telescope was launched on the 25th of December. I assume you were watching.
Yeah, absolutely. Absolutely. Heart in hand. It's like, do I have a career or not?
And I, obviously you must be keeping close tabs on it. So what has the telescope, been doing? I guess it's been almost a month now.
Yeah, absolutely. It's been a while. So the telescope has really cleared most of its major deployments. There's a period about 2.5 weeks after launch that, the thing to remember about this telescope is that it's really massive. And sometimes you see pictures of it and you really don't get a feel for just how ridiculously big it is. And the thing is because it was so big, it had to be folded up like origami, basically, to fit in. Even though the Ariane 5 is the biggest rocket we have, it still was nowhere near big enough to fit the telescope. It had to be folded up. So there was all this unfolding that's gone over the last 2.5 weeks. And some of these, unfolding maneuvers are dangerous in the sense that if they don't function, then the telescope won't function. And so it's basically done that. It's opened its sun shield, it's deployed its mirrors, and it's almost ready to go. The big next step is that all the scientific instruments operate at very, very cold temperatures for the reasons we talked about. You don't want internal glow on your camera. You don't want to look at the glow of your own camera. And so that's kind of the next thing. Now that most of the unfolding's been done, the instrument package is going to be opened up to cooling, and it's going to take a month or two to really cool that down to the temperatures we want to operate at. But at that point, then we can really start to take really spectacular images.
I can't wait to see the first images.
Exactly, yeah. I mean, the 20 years that it took Of course, we've discussed this on the past show as well, but the 20 years really were required probably to build it.
Yeah, I mean, it is an engineering marvel, and it is a long time. But of course, one of the things about these missions, people say, why do they take so long, and why do they cost so much? Is everything, every bolt, every nut, every thing attached to that telescope has been designed, redesigned. It's been torture tested. It's been deployed. It's been undeployed. It's been just tested because there's just no do-overs, right? Everything has to work. And so it's been a long journey, but, you see the payoff. And a lot of people, one of the discussions at NASA has been, everyone's kind of laughing because everything's going so well. They're like, wow, that was easy. People worked on this for 20 years. They're like, yeah, it looks easy because I spent 20 years making sure it was going to look easy, but that's really where all the time goes, is making sure there's no problems.
Precisely.
Yeah. And I also saw that due to the phenomenal job that Arianespace did with the launch, that they're estimating that the telescope's predicted lifetime is, maybe 20 years instead of 10 years, which I'm sure is very exciting for everyone.
Yeah, absolutely. Yeah, it's really been a dream. The rocket as well, the Ariane rocket has always been a very reliable rocket. It's had very, very few failures. And yeah, the ability, when you think about the level of precision that's required and, accelerating this incredibly remember, folded up, the telescope is still the size of a bus when it's folded. Take something like that, blast it out of the Earth's atmosphere, and put it on a trajectory in both the direction it's going and also the velocity it's going to, precisions to within parts in 100, better than 1%. It's an incredible engineering achievement, right? And it shows you, it just makes you proud to be a part of it, that people have developed technology that can do that.
Which is amazing. So as a Canadian observer, do you get to pick targets?
In principle, we do, and that was part of the planning. We've now chosen. We were given the time and said, what do you want to look at? So there's a couple projects I'm part of. We actually got our own time as well. The big project, that's the guaranteed time in exchange for the instrument. What we're looking at is some very massive galaxy clusters that are not very far away. But one of the things about really massive galaxy clusters is they provide this effect called gravitational lensing, which is a magnification of objects behind them. It's kind of like, I don't know, gravity is, the gravitational field distorts the passage of light past it, and so it magnifies distant objects. And so our goal to find some of the most distant objects is not only will we use the power of Webb, but we will use this additional magnification effect of these galaxy clusters to really see super duper faint things. And so the big project that we're doing, looking at galaxies, is looking at looking behind some of these galaxy clusters for distant galaxies.
Ooh, cool. All right. Connor, Ksutich, do you have any other questions?
Well, I can go on forever, but I will just shut up. So yeah, no, thank you.
Yeah, it was my pleasure.
I think I might have one more if you're willing.
All right, go for it, Connor.
So if the telescope always has to be pointing away from the sun, I assume this means that you can't just look at anything anywhere in the sky whenever you want. Like Hubble, you can point it wherever you want. But if James Webb has to be, with its sun shield facing the sun, I assume, there are certain times in the year where you can observe certain parts of the sky.
Absolutely. Yeah, you're absolutely correct, Connor. We can't look at any part of sky at any time. So there are what we call observation windows for certain targets. If you think about it, the way to think about the telescope is the sun shield is facing the sun and the Earth, and so the telescope is pointing sort of in the perpendicular direction. So if you think about that, it's kind of pointing either up or down, or diagonally up or down relative to that. And so as you move around, in the orbit, the 365 day orbit of the the year, basically, as the Earth changes and then James Webb changes position. As you say, you get access to different parts of the sky. But we're cool with that because that's actually how it works from the ground, anyways, in the sense that you can't observe any part of the sky from the ground anytime you want either, because the sun is moving and it's in front of your objects as well. So it's kind of a luxury that Hubble afforded you, as you said, to look anywhere you want, whenever you want. But James Webb is very much like from the ground. But we just wait.
Does it have any blind spots? Like any parts of the sky that it can't see because of the geometry of having the sun shield and etc.?
Yeah, it's a good question. No, every part of the sky is. You would think about it. You're like, surely there must be, and I agree with you. When I first looked at it, I'm like, surely this orbit doesn't give you the whole sky, but in fact it does. I'd have to give you a pen and paper, and we could draw it all out, which isn't very good for the radio. But I'll just ask you to trust me that indeed, you can see every part of the sky. There are certain parts that are much easier to access than others, and for example, there's a place that's called the CVZ, which is the continuous viewing zone. And if you think about it, that's either looking directly up or directly down for the telescope. Like if you think about the plane of the Earth and the sun, if you look perpendicularly directly up out of that plane or perpendicularly down out of that plane, you can see that any time of year you want. And so that's kind of cool. But in terms of no access, no, there's nowhere we can't see, but some places are easier than others.
Awesome.
So it's seasonal, like we just have to wait for the right time.
Absolutely. Except for the continuous viewing zone. You can view that whenever you want, any time of year. That you can always look up or look down.
Oh, okay. All right.
I guess it's the equivalent of like circumpolar constellations.
Mm-hmm. Absolutely.
All right. So Adam, thank you so much for joining us today, for taking time out of your Monday evening. This has been a really great conversation that I've really enjoyed, and I'm sure our audience has as well. So thank you very much.
Yeah, thanks so much for having me. It was fun to talk to you guys.
Thanks, Professor.
All right, take care. All right. We've got just a few minutes left in our show today, about 8 minutes. So I will quickly do a reminder that every Wednesday we have Teletube. Head over to our website, observatory.info.yorku.ca, and click on Wednesday public viewing in Teletube for more details. The observatory team always has an interesting show prepared. All right, so we have time for probably one, maybe two, if we hurry. News items. Connor, why don't you go ahead?
All right, so I'm just going to take us through some of the fun space things that we can expect in this new year of 2022. So of course, we've got the usual good stuff that occurs fairly regularly, such as meteor showers. And then actually here in Canada, this year we get to experience two total lunar eclipses, one on May 15th and another on October 8th. Of the two, personally, I would go for the May 15th eclipse, as totality begins at 11:29 p.m. Eastern, whereas the November 8th eclipse starts a little bit later or earlier, depending on which way you want to look at it. Totality begins at 3:02 a.m., which is not really necessarily time that I would want to be awake. Plus, for those of us here on the East Coast, the moon will actually set before totality ends. However, if you're on the West Coast, the moon will in fact be up for the whole eclipse. This summer, mid to late June, we'll see a 6-planet alignment: Mercury, Venus, Mars, Jupiter, Saturn, and if you are in really good observing conditions or just have a really good telescope, Uranus, and the moon, of course, will all appear in a beautiful line across the night sky. Of course, also this summer, we've got the James Webb Space Telescope data, the first data coming in, I believe, July. Then late September, early October will be the impact of the double asteroid redirection test. And this was that mission that was launched last year to explore the effectiveness of basically using kinetic impacts to redirect an asteroid. We don't have a concrete date as of yet, but the collision is currently planned to happen at some point between the 26th of September and the 2nd of October. And finally, we have more activity from all the various commercial spaceflight companies. Virgin Galactic is planning to launch its Unity 23 mission, which is actually a research mission for the Italian Air Force. So there'll be several Italians joining the American flight crew on that one. Blue Origin is aiming to have its first launch of the New Glenn spaceship in Q4 of this year. And then finally, SpaceX is hoping that SN20 will perform the first orbital flight of Starship.
Definitely a lot of amazing things to look forward to this year. Are there any in particular that you're looking forward to, Connor?
The planetary alignment, I will say, is always fun when you're up at the observatory, when hopefully we'll be able to do public events again soon. Just being able to set one telescope up on the Arboretum parking garage and just be able to point at all of the planets one after the other. That's always fun.
Oh, definitely. I remember the alignment. I don't think it was this many. It might have been only 5. I don't remember. But in the early 2000s, around the 2002, 2000, no, it was 2003. And there were always so many people. Like every week, there were more people as word spread. It was so great to get to talk to so many people about astronomy, about space, the planets. How about you, Kshitij? Any one of these events that you're looking forward to in particular?
I think I will really be, this time, watching the Virgin Galactic thing closely, because it seems more like a mission this time than just someone who has money just going into space. But yeah, and then the other thing is the planet alignment, of course, as I am a part of the observatory team, so I hope to be able to be there at the right time, the right place, and watch it myself, like with the telescope, not just like that. So yeah.
Nice. All right, we've got 3 minutes. I can do this. I can put in this last news piece. Okay, so this is kind of actually news-ish, because I somehow missed it back in November. Maybe I'm not the only one. So we know that there's lots of commercial space companies popping up all over the place, aiming to do it cheaper. There have been a number of different strategies used to achieve this. And have you heard of the company Spin Launch, guys?
No, and I think you should
before
listen to this.
All right. So it's a mass accelerator is their approach. So they have a facility that they've built called Spaceport of America in New Mexico, and they have a thing called the Suborbital Accelerator. It's like their proof of concept. It's a third scale version of the orbital launch system that they hope to build. So it measures 33 meters in diameter. It's just a bit taller than the Statue of Liberty. It looks like, if you picture like a measuring tape with a few inches of tape extended and stood on its end, kind of what it looks like. And you spin a rocket till it reaches a speed fast enough to launch the thing up into space. And last October, they did a test and it was successful. So I misjudged the amount of time we have, but maybe I'll put this into next week so more details can be given, or you can look it up yourselves. Thank you everyone for listening tonight. You have been listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. Your hosts this evening have been Kshitij, Connor, and myself, Julie. Stay tuned for Astronomy Night in Canada. Coming up next is Quirks and Quirks, Western Worlds, and Science for the People. Have a good night, everyone.
Good night.
Good night.
We hope that you've enjoyed this program from AFM Radio.